Welcome to another lecture on molecules in motion. If you remember, in the last class what we did was we had talked about the Debye-Huckel-Onsager equation. We had talked about the Debye-Huckel-Onsager equation in terms of the two effects which generate which cause which is associated with the ionic atmosphere of iron, which is under the influence of electric field. The two effects were the electrophoretic effect and the relaxation effect, and we had shown that the lambda, the molar conductivity of a electrolyte when at any concentration can be given as lambda lambda at any concentration lambda m will be equal to lambda m naught, that means contribution of at the limiting conditions of 0 concentration of the electrolyte is equal to minus A plus B into the molar conductivity in finite dilution into root over C. So, what we have derived in the equation, which here we have the equation. So, if we derive that equation, we can see that the equation which we are having is the modification of the Debye-Huckel equation, and this was called the Debye-Huckel-Onsager theory. And now, what we will look for the verification. What we will do, we have taken the limiting slopes of the lambda versus under root C curves and see whatever the values which we are getting from the equation which we have generated and what we are getting when we are doing the experiment. So, what we are trying to do? We are trying to model the equation in terms of what we usually observe for a particular type of electrolyte in a solvent system. So, here we are having a comparison of the data of the values predicted by Debye-Huckel equation in several salts, and the agreement which we are going to be seeing here. You see, this is the conductivity versus the say concentration term, the molar conductivity plotted in the y, under root C the molar concentration of the electrolyte in the x axis. See, for a various types of electrolyte system. So, if you have various type of electrolyte system, whatever we are seeing as these lines, these are the values which we are getting, which we are generating from the equation of the Debye-Huckel. So, if you see the agreement of whatever we get from the theoretical values generated from the Debye-Huckel-Onsager theory or equation, and what we observe are more in parity when the concentrations are lower. In fact, the agreement is usually very good in very dilute solutions up to say a concentration of 0.02 molar. Okay. So, and at higher concentrations, when the concentrations are much higher, which we have also discussed why the concentration is going to if we increase in the concentration, the operative retarding forces are much more. So, the equations which we are developed for the Debye-Huckel-Onsager equation has a deviation. So, we see at higher concentration the observed value are different from that of the experimentally predicted. So, what we can see in another diagram, I am going to show you the same thing, but in terms of the ionic strength. What Debye-Huckel studied was the mobility or the coefficient of activity in terms of the ionic strength, and ionic strength can be obviously related to the molar concentration. So, it is going to be directly proportional, right. So, we are going to whatever we have predicted for the de-Broglie theory, let us see how it can be extrapolated when we are talking about the de-Broglie-Onsager equation. According to the Kohlrausch's law, the slope of the molar conductivity, that is lambda m versus under root c curve, is predicted to have under root c dependence on the molar concentration of the electrolyte, and it also depends on the type of charge. It is not actually dependent on the actual identity of the charge involved, but it depends on the type of charge the electrolyte has. Okay. It is +1, +3, +4, what is the type of charge it is having. So, according to the Kohlrausch's law, the molar conductance is going to be dependent on the under root c concentration of the electrolyte, and it is going to depend on the type of charge of the electrolyte involved. For comparison between theory and experiment, we can see that the agreement is quite good, as in the previous slide also I had shown, at lower ionic strength. If you have lower ionic strength, it can be corresponding to lower molar concentration. At lower molar concentration, say 10 to the power -3 molar, and also on the type of charge we have, you can see the straight lines are actually what is predicted from the equation, and these are what we have actually in the observation when you do a experiment. So, these lines which are having the dots on them are the experimental observations, and the solid lines for the different electrolytes are given here, and we are extrapolating the line to the limiting condition of 0 ionic strength, which is going to be corresponding to approaching 0 molar strength concentration of the electrolyte. So, you see that the validity of this equation is quite good, whatever we have predicted, as long as the concentration of the electrolyte we are using is small. Okay. So, at limiting conditions, you at very low concentrations of the electrolyte, the equation which we have developed as de-Broglie-Onsager equation, which is having the contribution of the ionic atmosphere taken into account, which is having associated effects like electrophoretic effect and the asymmetry effect associated with it. So, these two parameters taken into account, we have developed and formulated the equation of de-Broglie-Onsager theory, and that theory, when we plotted against to compare against the experimental observations, we see that for 1 electrolyte, you see the at lower concentration the parity is quite good between the experimental and observation. And usually if you have a higher the type of, depending on the type of charge, you will have the different slopes of the conductivity which is associated when you are doing the measurement. And the concentration, whatever you are measuring, the concentration if is low in the range of 0.02 0.01 molar concentration of the electrolyte, then we for any type of electrolyte the parity is quite good. Okay. This is the validation of the law which we have taken time to formulate. Okay. Now, we move on to something different. So far we have talked about the ionic atmosphere, the ionic motion of the molecules. Now, we are in the position to extend the discussion of the ionic motion, whatever we have developed, to cover the migration of neutral molecules or ions in absence of an electric field. We shall do that by expressing the ion motion in general way, not like the earlier one, and then discover that the same equation which we have applied previously can be actually extended to a charge particle which of a particle of charge particle of 0 charge associated. So, that means a neutral molecule. So, what we are trying to say that whatever we have discussed for the charged molecule under the electric field, we will try to express the motion of the charged particle with having no charge associated with it, charge on it being 0, considering as a neutral particle, and we will generalize and formulate how that can be applied to a system which is say having no charge associated with it. So, for that we will take up verifications and generate few laws which can associate, which is a link between the discussions on the ionic motion of particles in migration in a electric field to the migration of a neutral molecule in absence of a electric field. So, one of the things which we will try to verify is the Fick's first law of diffusion. So, what happens in if you have the mobility of ions in electric field, there is a connection between the mobility of ions in electric field and at the rate at which the ions diffuse under the electric gradient. Okay. So, what we have so far developed, we have developed the mobility expression and we have developed the mobility expressions in association with a electric field. Now, we will see that we can relate conceptually the mobility of ions. Instead of that, we can say the diffusion of ions can take place if there is also a concentration gradient associated. On thermodynamic grounds, a particle is expected to spontaneously move from a higher concentration region to a lower concentration region. That means, thermodynamically any ion can be having a driving force of the to move forward or migrate depending on the concentration gradient it is associated with. So, the driving force for the motion of these small particles will be proportional to the negative gradient of the concentration of the ions in the medium. Okay. So, it is always the ions are going to diffuse from a higher concentration region to lower concentration region, and the driving force of this movement of the migration of the ions will be proportional to the negative gradient of the concentration, and velocity of the particles hence are supposed to be proportional to the driving force, because whenever you are having particles moving, the motion is guided by a thermodynamic force. Any movement which is going to be associated with that will be the speed of the molecules, hence should be also proportional to the driving force. So, if the force of driving force is more strong, the speed of the particles moving should be migrating should be more associated with it, right. So, let us now come into the discussion of a flux of particle. Fick's law, what does Fick's law says? Fick's law says, first law of Fick's law state that the particle flux is proportional to the concentration gradient. This can be deduced from the kinetic model of the gas. Let us see how it can be deduced in more general form, and it can be applied to diffusion of species in the condensed phase, that means the liquid and the solid phase as well. So, whatever concept we had developed from the kinetic model, we are going to be using the same concept to deduce use it as a generalized concept to deduce the diffusion of species in a non electrical under no non electric field, no electric field associated, and also for species which is actually not charged, or it is movement of the particles in the solid or liquid phase. So, let us suppose what we have so far, the flux of diffusion of diffusing particle in motion in response of a thermodynamic force arises from a concentration gradient. So, let us assume that this is the first assumption we are going to think of, that the flux of the diffusing particle in which is in motion is in response to the thermodynamic force arising because of concentration gradient. This is known to us, we have known that this is the phenomenological equations which we have already had. So, we are going to assume that. Now, next one, what we have already done, we have previously shown that the particles move with a terminal speed when the thermodynamic force matches with that of the viscous drag associated with the field. So, if you remember, the thermodynamic forces is going to be matched with the viscous drag, and then the speed associated with that is going to be known as the drift speed. So, the particles move with the steady terminal speed or drift speed when you have the thermodynamic force balancing the viscous drag. So, this was the concept we had used when in application of electric field, but we are not talking about the electric field here. We are talking only about the particles moving in a viscous medium, and if they are supposed to be moving, then it is essential to have, if they are moving with a steady drift speed or a constant speed, and this speed is known as the drift speed or terminal speed. This speed should be can be achieved by the particle only when the thermodynamic forces operative on the particle is matched by the viscous drag associated in the medium. So, this is the expression we have. So, we have the frictional the force, which is thermodynamic force, is going to be proportional to the speed of the particles. So, this is what we can write. So, we can write the drift speed is proportional to the thermodynamic force, because if the thermodynamic force is balanced by the viscous force, only then you will get the achieve the drift speed for the particle which is associated. So, S is going to be proportional to the F, the thermodynamic force which is operative on the particle, and this is the speed with which the molecules or ions or whatever we are looking into particles are moving with at a steady rate. Okay. Now, again we have a relation where the flux of particle is proportional to the speed of the particle. If you remember, we had talked about the flux of a particle, how it was defined. Suppose we have a number of particles associated with the system, be having a concentration C moles per liter. So, if we want to find out the number density, we had taken, it is going to be concentration into the number of Avogadro number will give you the number of particles associated with it. So, the flux of particles which is moving with a speed s in the say any x direction in the time interval delta t, passing through a window of area A will be divided by the area of the window and the duration of the interval delta t is going to give you the flux of the particle. So, S delta t into A is the volume element which is containing the total number of, this is the volume element, area into this was the distance, speed into time was giving in the distance. So, this was the volume element in which the particle, the total number of particles in the volume element of this was considered, that into the concentration of in moles per liter into the Avogadro number gives you the total number of concentration of the particles, that divided by the area into the time delta t gives you the flux of particle. So, if you see these are going to be cancelled off. This we have already derived previously for a gas system when we are talking about molecules moving in the gaseous medium. We have done that. We have also seen how this equation gets modified by a new value here when we are having an electric field associated. So, for we have taken we have also derived the flux of ions, but we let us only concentrate on the flux of particles. So, flux of particles, as you see, will be proportional to the speed of the molecules associated in the system. So, we have what we have generated? We have generated another relationship of dependence, where the flux of particles represented by J will be proportional to the speed of the particle. So, this is the drift speed which we are talking about. So, J is proportional to S, right. Now, again we go back to the phenomenological equations which we had. The driving force of the molecules of a particle F will be proportional to the negative gradient of the concentration. So, if C is the molar concentration associated for a particular system, and if the particles are moving say in the particular x direction, then the driving force which is going to drive the molecules to or particles to move along the medium, the migration of the particles will be proportional to what? Will be proportional to the gradient in concentration, negative gradient in concentration. So, negative gradient in concentration is actually given by minus d c by d x. That means, we are talking about the movement of the particle in the x direction. How the concentration of the particles are changing when the particles are moving in the x direction, and in this x direction what we are looking into, what is the driving force for the particles to move along the x direction. It is the concentration, it is the driving force is the concentration of the difference in concentration along the x axis. So, the particles are going to move from a higher concentration to a lower concentration. So, the driving force is proportional to the gradient, negative gradient in the concentration. So, what we have? We have generated three chain of proportionalities. The drift speed being proportional to the driving force, which we have from the drift speed being attained only when the viscous drag and the thermodynamic forces are balanced. So, it is going, the speed which is associated will be proportional to the thermodynamic force which is operative. Then we have seen the flux of particle which is moving in a medium should be proportional to the speed with which the particles are moving, the terminal speed, and we have seen that the thermodynamic force which is operative for a migration of a particle along a medium will be depending on the negative gradient of the concentration. So, if you see here, S is proportional to F, J is proportional to S. So, what we can say? We can say that S is proportional to F and F proportional to J, and J is proportional to, can be taken as proportional to the change in concentration. So, what we have? We have derived the expression which is the flux of particle J will be proportional to the concentration gradient along the medium. Okay. So, what we have in the form, we have generated the contents of the first law of diffusion. So, the first law of diffusion says that the flux of particle will be proportional to the negative gradient of concentration when the particles are moving along the x axis. So, the chain of proportionalities which we have generated, see these equations we are not saying is it is not over this lecture that we have developed. We have developed the speed of the particles being proportional to f when we were discussing the particles moving under electric field. That time we said that the electric field will be balanced by this thermodynamic force which is acting, but eventually what essentially means that when a particle is moving with a steady speed, steady or constant speed, it has to have a condition where the viscous force and the thermodynamic forces are going to balance. So, that concept was already there, we have extended that. Now, we also considered when we are talking about a particle, it need not be charged. We say that let it be a say from kinetic theory whatever we have derived, any particle moving in a particular medium. So, if their particles are moving with a particular speed, then the flux of that particle was found to be proportional to the speed of the particles in the system. And again, from the thermodynamic expression of thermodynamic force, which is supposed to be proportional to the gradient in the number of ions or number of molecules of particles in a system, these three proportionalities, if we combine, if we take the analogies, then we come down to the fact that the flux of particle will be proportional to the negative gradient of concentration. So, I think we will discuss till this today. We will talk about the other equations in a later class.